You might recognize this ball from our very first video. This ball is like a curve. And this is a ruler, and a ruler is like a line. So what happens when a line just touches the ball, or the ruler just touches the ball, at just one point, or a line just touches a curve at just one point? Well, we have a name for that. The name we have for that is called tangent. This line is tangent to the curve because it touches it at just one point. My question is, how is the tangent line similar to the curve, and how is it different? Well, this is climb time, and in this video, we're going to look at tangent line approximations. So you see we have a curve, this green line right here. We have a curve, and this would be our function. We call it f, or f of x. And then we have this pink line, and this pink line is tangent to the curve. It's hitting it at just one point, and it's tangent to the curve at A. We'll say it's tangent to the curve at A. So what do the function and the tangent line have in common? We're going to call the tangent line L, or line. So the pink line is L, and the function curve is F. So what do they have in common? Well, it turns out they have two things in common. So they have two values in common. We want to look at both those values. Maybe you can predict what those two values are right now as you're looking at. So what two values they have in common? Well, the first thing they have in common is because the pink line touches the green curve and they intersect at that spot, that means they're going to have the same y value. So that means f of a is going to equal L of a. So I'm going to just put that in blue because they have that in common. So f of a, that's also going to be the same thing as L of a. So the first thing they have in common is they share a point. And the point they share is the point of tangency. That's the definition of tangency, that they touch at just one point. So therefore, we'll say L of a is going to be equal to f of a. So they have the same point there. So L of a and f of a are the same. So at the point A, they have the same y value. Now there's something else they have in common. And the other thing they have in common is that the slope of the tangent line on F, which is this line right here, is going to have the same slope as L by definition. So the way we write that is we would say f prime of A, that's how we say the slope of the tangent line of f of x at A. The slope of the tangent line of f of x is equal to, and I don't have a great way of writing this, so I'm just going to say slope of L, slope of the line L. Okay, so if you come up with the equation of line L, it's going to have a slope, and that slope is going to be the same slope as f of x. So they have two values in common. They share a point. They share the point where they're in common, and they also share the same slope. The slope of the tangent line on F, and that's going to be the slope of F at a point, we call that the tangent line right there, is going to be the same as the slope of L. So they have that in common. So now, what do they have that's different? So we know what they haven't that's the same, but what do they have that's different? Okay, so if f of x is not a line, and what I mean by that is it's a curve. In this case, you can see that f of x is a curve. It's green. So if of x is not a line, then that means that they will not have the same y values as soon as we get outside of A. So then f of x is not going to equal L of x outside of A. Okay, so what I mean by that is if I go a little bit to the right and a little bit to the left of A, their y values will not be the same. However, it could be that the green one like turns around again and comes back down and eventually intersects L at another spot. So it could be that f of x is equal to L of x at other spots, but around A, close to A, they will not be equal. And you can see why they're not equal. They are spreading out from each other. So they are not equal. Okay, however, with that said, as we get closer and closer to A on the pink graph, then the y value will be very similar to the y value on F. So they will be kind of close to each other. So let's do another example. We'll call this B. And so we'll say this is B here. All right, so B will strike L in a certain spot. And if I make that come over here, I can say that this right here would be, let's see, we could say this is L of B. I like the different colors. It takes a little time to change out the caps, but that's okay. So this is L of B because that's going to be the x value B that's on the line L of x. And so that's its y value. Now, if I keep going straight up, I eventually will hit F, like right here. And if I go over on that one, it's easier for me to go left to right than right to left. Then that's going to hit F of x at a certain spot, the green one. And so this is going to be F of B. Okay, so you can see F of B is not equal to L of B. F of A is equal to L of A. These two are equals. This is equal to L of A because they share that point. So the function value on the pink graph is equal to the function value on the green graph because they share that point. So F of A is equal to L of A. But as soon as I move a little bit to the right at B, B is going to intersect this line L at a different spot than it's going to intersect the green curve F. So L of B and F of B are not equal. Okay, so that's why I say F of X is not equal to L of X as soon as we move outside of the point A. So move a little bit outside the point of A, a little bit to the left, a little bit to the right. They are not going to be equal. Now, when I say that, I mean very, very close to A because, like I said, it could be the case that F turns around, comes back down again, and intersects L at a different spot. But very close to A, they will not be equal. But even though they're not equal, they will be close to each other. So we can write this down. We can say as B approaches A, so that means as B gets closer and closer to A, then we know that L of B will approach F of B. So as B approaches A, L of B approaches F of B. And so what that means is L of B will be approximately the same as F of B when B is very close to A. So when B is close to A. So while they are not the same value, and you can see the pink one here and the green one here, those are not super close to each other. Okay, so there's a pretty decent gap there. They're not that close to each other at that spot. But that's because my B is way over here. If my B was much closer to A, then they would be very close to each other. The closer my B is to A, both on the right and on the left, the closer my B is to A, then the closer the y value on L will be to the y value on F. So as B gets closer and closer to A, L of B will get closer and closer to F of B, and L of B will approximate F of B, okay, as long as B is very close to A. So they will not be equal close to A, but they will be close to each other. And the closer B is to A, the better approximation the line on the tangent will be to the line on the graph. So why is that useful? Well, sometimes we don't actually know what F is. Sometimes we don't know F, but we do know something about the tangent line. So if we know the tangent line, we can actually try to approximate the y values on F based on the y values on L. So we can actually look and say, okay, well, if I know what the y value on L is, maybe I can just then have a good guess of what the y value in F would be. So if we don't know what F is, but we do know what L is, we can approximate F with L. All right, let's look at one more thing. We know that L of B is not exactly equal to F of B. They're close, but they're not exactly the same thing. So if they're not exactly the same thing, then which one's bigger? Is F going to be bigger at B than L, or is L going to be bigger than F? Well, as you can see from our graph right here, F is higher. The green one's higher than the pink one. So if it's higher, that means it has a bigger value, a bigger Y value, which means F is bigger than L at point B. Now, that's not always going to be the case. The reason why that works is because F is curving up. If F weren't curving up, then we'd get a different result. But because F is curving up, that's why F is going to be bigger than L at point B. So we have a name for curving up. That name is called concavity. It's concave up. And I have another video on that. If you want to check that out, check out the video on concavity. And what we've learned about concavity is it has to do with the second derivative. So if the second derivative of F at point A is greater than 0, that means it's concave up, then you know that the function value at B is going to be higher or bigger than the function value at B on L. Okay, so F of B is going to be bigger than L of B. So you can see that. So F of B, this green one, is higher than the function value L of B. You can see the green one's higher than the pink one. But that's because it is concave up. So if we had the opposite result, if it was concave down, if F prime prime of A is less than 0, so that means it's concave down instead of concave up, then F of B is going to be less than L of B. All right, and it'd be helpful to have a diagram of that. Let's show what that looks like. So we have a graph, and let's draw a concave down version of the graph. It looks something like this. That one is concave down. And then, since that one's concave down, if we did the tangent line to that, it would look something like this. And so while at A, they have the same point, they still share the same point. Actually, I'll make that one blue because they share that point. At A, if we move out from A to a B, you can see that they no longer share a point. In fact, in this case, the green one, F of B, is going to be less than the pink one, L of B. Okay, so this is an example here of something being concave down. So I might write those words in as well, just so that we are familiar with those terms. This is concave down, and this is concave up. Okay, so concave up was our original example here. Maybe we can draw an arrow to there. And concave down is this example right here. So if something's concave down, then they're going to be off from each other, but the difference is the function value will be a little bit less than the value on the tangent line. If it's concave up like this, it's curving up, then the function value is going to be a little bit bigger than the value on the line. But what if it's neither concave down or concave up, and F prime prime of A equals 0 instead of less than 0, greater than 0? Then you kind of have to analyze it a little bit closer, and you have to see what it's doing. Is it switching concavity? But it requires a little bit more analysis than what we have here.